How's it?
Hawaiʻi Pod, Hawaiʻi Tracker. Anna's over here to the side. We're setting up for the meeting tonight. Want to throw something out?
Yeah, welcome everybody. We are teaming up with Two Pineapples to bring you this first episode of the Volcano Awareness Month. And this one's going to be talking about faulting on Kilauea, and we're excited to see what we have to presented here today. So yeah, looking forward to it. Thanks for setting us all up, Lou.
Absolutely. Everybody just hang with us. I'm going to flip the camera around. Everything should be starting up in a few minutes. Thanks for joining us.
All right.
Aloha.
Aloha.
My next project, of which I don't know a damn thing, is our YouTube video, is that doesn't harm you. You have to have it. And it turns out it's the spiral block behind, and it's in the steering wheel, so I've got to remove the steering wheel and do this. And the YouTube videos are good.
It's so nice to see you guys all here. I'm Darcy Evans, and I'm here to introduce our wonderful speaker for the evening, Professor Steve Lundblad. And as you know, let's hear about it. Apparently everyone already knows him already. Most professors, when you think of a professor, it's someone who stands in front of a crowd of students and lectures to them or helps them in the lab, and that's what Steve does for sure. But in addition, what he does is he works on collaborative projects with the USGS Hawaiian Volcano Observatory. He does so many wonderful things. In his collaborative research projects, what Steve does is he brings his geology students from his campus out in the field with him to help collect the data so that the students get real-world experience. They're not just book learning. They're not just looking at PowerPoints. They're helping collect the data. And then that helps them go on to fabulous careers. Projects around the island that they can share with HBO and do an even better job of monitoring volcanoes. So it's a real wonderful situation. So he'll show some of his work. While I'm getting ready to hand Steve the microphone, I'd like you to notice some of the other events that HBO is putting on this month at different venues, and including 1 week from today, right here in this exact same room, Cheryl Ganseki, who also teaches geology here, will compare lava from 2018 eruption with more recent ones of Kilauea. So let's give a second round of applause to Steve. If you need to use the restroom, it's located near the elevators, and you can head up the back door to find that.
Hi, good evening. I never use one of these, so I apologize for being bad about probably using it well. Thank you, Darcy, and we'd like to thank the folks at HBO for inviting me to help promote Volcano Awareness Month this month. So there are these talks, and then there are also a few after dark in the park talks up at the National Park on Tuesday nights, right, Darcy? Yep. And so you can find their full schedule in there. So yeah, what I'd like to talk to you a little bit about tonight is kind of tracking faults and deformation that goes on up on Kilauea volcano, and it's in the area that's kind of south of the summit. Got some Velcro here, sorry. Yeah, that's not going to work. If you were coming looking for some sort of talk about, nice red hot lava, this is not the talk for you. But what we're going to do instead is talk a little bit about deformation of the volcano and kind of how that lava, magma moving under the volcano, kind of influences what happens. So that's kind of where we're headed tonight. I also have to do a little self-promotion. I'm fortunate to be able to work with the HBO staff and on collaborative projects with them. I was also very fortunate to work with Rick Hazlitt. Some of you guys know Rick. And he was the author of the first version of Roadside Geology, which I know many of you know, maybe have. And we have a new version of that. And so one of the great things that has changed in that book is we now get to use color. And so there are color photographs and there are color diagrams and everything's been updated. We've got information because a few things have changed here in the last 25 years. So that's just a little self-promotion. It's basically books in Hilo and various other retail outlets. So where are we looking tonight? Well, first of all, just a reminder for everybody. There we go. Okay, so we had an eruption in December coming off in the summit and coming down from the northeast rift of Mauna Loa down towards the saddle. We've currently got lava lake erupting in Kilauea, and we're gonna talk about an area that's just south of that. And to just zoom in a little bit, there are two main rift zones here coming off of the Kilauea volcano. I always tell my students that geologists are not super original when they come up with names. So the southwest rift zone is in the southwestern part of the volcano. And the east rift zone comes off of the east part of the volcano. One thing you might notice here is that the east rift zone has an interesting bend to it. It doesn't just come straight out of the caldera. And the one hypothesis for how that has occurred is that it actually was attached to the summit area, and over the last 100,000 years or so, it has migrated to the south. And so consequently, as it did so, we've got this interesting, what I think at least is an interesting area, to the south of the summit, which is this Kauai fault system. And so we're going to talk about these faults and this extensional area that is on the south side of the summit, in the summit caldera. So here's a cartoon that depicts a little bit, if we go from Mauna Loa up here on the north side, down through that out into the Pacific Ocean. Mauna Loa has built, or Kilauea has built itself up onto the top, to the flank of Mauna Loa. There's the summit caldera, and there are faults associated with that. There are certainly faults associated with the Hilina Pali and some of the slumping out to the south into the ocean. But we're really focusing on this area that's kind of in between. And so this is an extensional area with a whole series of faults across that. Here's a Google Earth image of that same basic location. And I think what you can see even on this is that there are a whole series of these faults that run through this part of the volcano. So I've added an important thing here to remind myself to talk about it. This is or at least a version of the lava zone hazard map on the Big Island. So if you're familiar with this diagram, that's great. Basically, the lower the number, the higher the risk of volcanic eruption. And it's based on how recently lava flows have covered certain parts of that volcano. So obviously places like the summit and the caldera are lava zone 1. It turns out that much of the rift zones are also lava zone 1. Areas just downslope from that are 2. We live up here in Hilo, we're in lava zone 3. If you go across the bridge onto Mauna Kea, you're in lava zone 8. Okay, so that's kind of the general idea. Closer to the active volcano, lower the number, more likely to have lava flows. Well, I've put a couple boxes right in here just to recognize that these numbers look like they're out of place. And this is one of the nice reasons why we can go to this particular spot and measure kind of a long-term motion on these faults. And that is that these areas are kind of protected by just the geometry and the topography of the caldera. The lava flows can't make it out of the caldera and go down to the south very easily. Instead, that lava is going to go through a couple of connectors, kind of out through here, and go out. Here's Mauna Ulu, which erupted in the late 60s and early 70s. Here's the southwest rift zone with some of these more recent lava flows out here. But notice that this area has lava flows that are actually quite old, on the order of 700 years. So consequently, we can still see what's going on these faults. So I've just got a couple quick things on here to point out. If we have active faulting, some of you fine folks are from California, if you have active faults, you can find the fault scarp. And the topography actually represents how much motion there's been on that fault. If we instead go to some place where the faults are old, okay, that topography, this is some picture I found, right? They're making, I think they're putting in a new set of something, right, in a quarry or whatever. This topography really doesn't reflect how the fault was moving necessarily, because so many things have happened since that fault was active. So this is really a great place to be able to go out and look at these fault scarps and see what's happening. And so one of the things we do, both in our classes and also as part of this project, working with the Hawaiian Volcano Observatory folks, is we have the students out actually looking at what the faults look like and trying to measure them and trying to figure out how they change from one place to another and what type of motion is occurring. So this is a great place to do that because they haven't been buried by lava flows. Oh, wait, that's the right one. Okay, so let's take a look at some of these faults. This is the southern fault of the system, and many of you, if you think about it, you've seen this, may not have recognized it, but that's okay. This is the Hilina Pali Road, and this is the campground that's a few miles down the road. And gee, look at that. That looks like a big cliff, and that big cliff happens to be one of the big faults, right? So here are the real stars of the show. These are some of the students out helping to make some of the measurements, and we'll talk more about that. This is what happened in 2018. So we had a big magnitude 6.9 earthquake along the southern flank of the island. We had collapse at the summit of Kilauea, and we had 2 months of repeated collapse and earthquakes associated with that. And sure enough, something happened right in there. And so these are active faults. These are faults that are moving. And so we're in the process of trying to measure those to add to some of the general volcano monitoring that the HVO folks do. And so we're trying to measure how much motion there is. And of course, it's always difficult to measure how much things move when they're still moving. So this is always a little bit of a snapshot in terms of what's actually happening at a given place. Right, Mickey?
Yes.
Right, so Mickey is the star of our show tonight. She's one of our graduates. And these are big faults, or at least some of these, right? So this is a little, this is a different one of those faults. And you know, this, I think everybody can hopefully recognize where the fault is in that photo. I like this photo. This is from this fall. Here's Natsumi down here. She's about 25 feet below me. And it's kind of hard to tell with on the screen with everything, but this is the cliff that goes down 25 feet. And then on the other side, it's going up about 10 or 15 feet over there. So this is a little down-dropped block in there. And there's motion on that fault that's continuing. Okay. So how does this fit in with what the professionals do? Right? So the HVO folks, it's their job. They do a very good job of monitoring and tracking what's going on in the volcanoes. And they have a series of various types of monitoring stations. They measure things like earthquakes, so there are a bunch of seismometers out there. Those are these nice triangles that are in various places. They have some permanent GPS stations that measure how the ground moves. And so here's, those are the stars, and here's some different kinds of motion that they see off of that. They have some things called tilt meters, which measure tilt. That's right. They measure how much the volcano tilts. Okay? And then there are gas measurements that occur as well. And it's not surprising that many of those instruments are clustered around the summit of Kilauea, because there's a lot of activity going on. There's also a fair number of instruments at Mauna Loa, and this is how, almost as if by magic, the HBO folks can say, hey, we think there's going to be an eruption in a couple hours, right? Because they're monitoring this stuff, all the time. So we're going to try to add to what's going on, or kind of re-supplement what's happening with these various stations. I'd also just like to point out, here's a little plug. If you go to their webpage, if you don't go there regularly, what are you doing? No, yeah, you don't go there regularly, but this is actually information that you can find, right? These are just screenshots from clicking on one of those various stations. So you can, if you felt an earthquake, you can go and see it, right? And you can see how the ground has changed, right? If you understand what you're going through in here, you can have a look at it. It's a fabulous resource. So with this information, maybe some of you have been to some of the talks given by folks at HBO, right? But they can figure out a little bit about how things are going on based on that GPS information. How are different parts of the volcano moving? Lava as it's coming out, or the magma as it's pushing up from the volcano is causing the ground to tilt in different ways. Another kind of high-tech thing that happens, satellite imagery, and there's a kind of an interfered ground that can be made, and you can kind of make some sort of a model on how the ground is actually forming. Okay, great. Well, we go with a little simpler approach. So this is, again, Google Earth image, slightly different one maybe than the one we looked at before. Here's the faults running through here again. And now I've put a whole bunch of different colored dots of various types in here. And we're making direct measurements on these fault systems, or on these various faults and cracks that are out there. And we've got kind of 3 different sets that are out there. These are all, many of them were put in a long time ago. Some in the 60s, some in the 90s. And Don Swanson, who many of you guys know, and some other folks in the 60s kind of were forward-thinking enough to say, we need to put these out here so that we can come back and measure how the ground moves. And I think it really shows the power of this long-term monitoring of some. For those of you that are young, you may also not realize that we didn't have GPS in the 1960s. And so we didn't really have this, we didn't have satellites that we could do all this stuff for. So it really, this was the way in which you could measure. Okay? So there are kind of 3 things, and we'll just point out here. So there are these things called crack stations, which are the squares. They're kind of hyper, so we'll look at them, but lots of, or several different monuments right in a close proximity to one another. Level lines, which are surprisingly these line-like features that go across, and that's just a series of regularly spaced monuments. And then I just will point this out because Tegan's in here someplace. I was gonna call her out. So we're gonna work on a project with her where we're gonna try to go out and kind of remeasure with some GPS units these electronic distance measuring network to find out the distance between those points and maybe see how they've changed over the years. So it's direct measurement of these things. So what are we looking at? Well, we're looking at things like benchmarks. Some of you have seen benchmarks before. So here's a nice shiny USGS benchmark with a nice X right in the middle of it. And what is it? Well, I've got one. It's basically that brass top. But the important bits on this are that it has a base to it. So you drill a hole into the rock, because you want it to stay in the same place. And then you cement it in, so it stays in the same place. So when the ground moves, the monument moves with it. Simple, actually. Nice. There are also out there a bunch of stainless steel carriage bolts that have been cemented into the rock. And thank you, Don, wherever you're hanging out right now. They've all got tags on them so we can figure out which one's which is really important. So just, one of the things, one of the kind of the take-home messages for this in working with the students is to get them all to work together. One of the things we do is we look for those quarter-sized pieces out in the middle of the desert. Okay, that doesn't sound terrible because we kind of know where they are and we have GPS points for them. We can do that. I just want to point out that we do not paint, we haven't painted things in the park. This is actually down in Lower Puna. Finding benchmarks in places that are highly vegetated, it's a challenge. And so part of this is we always painted the edges of them so that we could try to find a little bit of orange paint buried in the vegetation that grew since the last time we were down there. So finding these locations is actually important. And in some of these maps that I've shown you, there are places that we just don't go anymore because they're so overgrown that there's no way we're going to find them again. Right? But we have to find that specific spot. That's the take. Wrong one again. Come on, Steve. There we go. All right. So one of the other things that I guess I would point out is that we live in the world, and at least with my geology students and as part of this project, of very high precision, and we'll talk about that in a second, but really low technology. So we're not dependent on satellites, and we're not dependent on electronic tilt meters, and we're not GPS units and everything else. We're not worried about that. We have two main components. One component are these nice 3-meter high rods. We don't do this during lightning storms. We'll talk about the precision involved with those in a minute. And then I have essentially a very nice optics telescope that I level so that everything's nice and level. And I'm just going to look at what's going on with these guys. So those rods, here are a couple of people that are meditating out in the field. These are a couple of our former students. And they're trying to keep that rod nice and level. And there's a bullseye level bubble on the back. Pretty straightforward. And the reason why this is in here is you can see there are two sets of numbers that are exactly 1 centimeter apart that go up through the middle of that. And the center piece is actually a piece of metal that doesn't expand and contract, so that is always 1 centimeter in distance. Also notice those two scales are slightly offset from one another. And that's because we take two measurements for each reading, or two readings for each measurement. And that's kind of to do some quality control. So here's what we do. As if by magic, a red line shoots out. No, there are no lasers involved. So I look through the nicely leveled telescope. There's a way to, it's physics, we won't worry about that. Measure the space in between each centimeter. And that's really the great part of the instrument that I'm looking at. So for example, Will is over here and I'm going to take a measurement, so you know that we're talking about some precision here. It's 123.102 centimeters. So that's 123 centimeters, 1 millimeter, and 2/100ths of a millimeter. Okay? Now, obviously, there's going to be some error involved, and those errors kind of cancel out and various things. But these measurements can be very precise, down to less than a millimeter. So I'll take the measurement over here, and then I'll swing over and take a measurement. I think that's amber down there. hiding. I don't know. And I take a measurement over there, right? And then all I'm going to do is subtract those two numbers from one another. And so now I have the elevation difference between where the bottom of that rod is and the bottom where the rod is over there. Now, one other point to make here, which I think is, again, shows really the elegance of where all these monuments or pins are. Can everybody see a fault in that picture? Yeah. Okay, right? So there's a big wall over there on the left. So that block has moved up relative to the block that we're standing on. Turns out that I'm actually on a block that's higher than where these guys are standing, but we won't worry about that right now. Whoever it is, they're hiding behind the rod. Who is that? Maybe it's Christine. Oh, I think it is Christine. Anyway, okay. She's on the other side of the fault. So we don't have to go to the top of the block because the whole wall has moved up together. Right? So part of the downside of this method is that I have to have line of sight level or measuring. So I can't just turn it and look up to the top of the cliff. We also measure distance. We measure distance with a very, very high-tech piece of equipment. A 50-meter steel tape. Right? Pull it tight. Do it the same way every time. And again, surprisingly, maybe to some people, this is actually a very precise way to do this. We can get to within a millimeter or two when we remeasure things. So again, there's a technique to it, and all of our students are basically very good at this. They're experts at this now. I don't even have to talk to them about it. They just go do it. It's very nice. Right? So these folks are out, pulling this tight, and we're measuring the distance between the points. So we just do this in a bunch of places. We're trying to compare notes with what happened before, and we can see some movement, especially on some of these faults, from year to year. Okay. So just a little background as well, but also a little bit about how things move, or how the different ways that these faults move. One way that these faults move is they creep. In other words, if I come back 3 months from now, I'm going to see a little bit of motion. If I come back 6 months from now, I'll see kind of twice as much motion. If I come back a year from now, I'll see a little bit of motion. Other faults kind of stick and they don't move much at all until something happens like an earthquake. And then they move a whole bunch at one time. Okay? So this is actually one of the old sites. This is one of the original sites near the Chain of Craters Road. And you can see this is just a graph, and one goes up, one goes down, but the idea is that the relative motion between point A and point C, or point B and point C, is such that it's creeping a little bit all the time, right? And it's moved 25 centimeters in the last, whatever that is, 55 years. And so many of these stations were put in after this big event, earthquake, magma intrusion, eruption, around Christmas time in 1965. So in 1966 were the first measurements on some of these stations. And so again, the power of this long-term monitoring. And some of you folks maybe know this place. You might not recognize it, but you can look for it. The park does a nice job of repaving their roads, though. So sometimes, even though the roads move, then they repave it. You can't tell so much anymore. But this is the vault crossing the road, and this is right down below where the Hilina Pali Road goes off to the right when you're going down the Chain of Craters Road. Interestingly, to me, again, it's a little bit of you kind of have to look for it. The fault runs right through here. And here's the fault going right through here. We're measuring with the tape, and we got the rods ready to go and everything. This was right after the 2018 rush. So there was actually a crack, and then the folks at the park drew around it, okay, because they're going to fix it, right? Well, the fault is actually over here where these folks are standing. So the question is, well, why is there a big crack in the road right there? Well, if you look closely, and I didn't take a picture for this idea, but it shows up. If you notice, there's also a crack over there. Turns out they put a steel plate underneath the road. So the steel plate basically acts and then stuff moves on the side. It didn't stop the fault from moving, so that's the part. So you can see those cracks up there because they recur as this fault continues to treat. All right, so what do those crack stations do and what do they look like? Well, again, there are a bunch of them, you know, surprisingly or not, near some of these cracks, near some of the main faults. And there are several different points, generally. So this is a fairly simple one here at the station 98.8, which is on the main poly down here in the southern part. Okay, so a little bit hard to maybe understand what this graph represents. Here are 3 pins, A, C, and B. There's also a B, it's not on this graph. So between 1998, when it was put in, this is station 98-8, in 2003, the relative motion between A and C and D looks like that. In other words, not much at all. Between 1998 and 2011, so in other words, kind of, if you just look at the difference between the square and the triangle, right? So between 2003 and 2011, there's a little bit of motion between these guys, but really not much. Now, this makes it seem like it happened over a long period of time. Between 1998 and 2018, those are the differences. And so you could think, well, here's the amount of offset between 2011 and 2018. But my guess is that all happened in 2018, right? And so this is about 40 centimeters, right? 1.5 feet, right? Of offset along that fault. Okay, so I made some note of this, and you know, we were talking about you know, this nice big cliff. There's part of this same fault that's out further to the west that is, I think it's 15 meters high, so it's 50 feet, right? In 700 years, that's how much offset. So I made some comment, as I am often known to do, about how, oh, well, you know, there's a lot of offset on these big bounding faults. And Don Swanson looked at me and said, well, how do you think they got to be that big? I mean, right? Hello? Yeah, and so these are the ones that have the most offset on them because they're the big faults, right? I mean, that makes some sense. It's obvious, but it kind of, at least for me, it took a while to see. Okay, so we can get detailed information about how the fault moves. And so I'm just going to show you a little more complicated spot. Here's a different crack station. And again, the point to make here, not that you care about what's going on with all this stuff, but just recognize that there are a bunch of cracks. There's a ramp. There's a bunch of pins out there. The elevation difference between A and G is about 25 feet. So this is a pretty big fault. And it also moves in a couple different ways. And so here's a picture looking along that, I think. And so top's up there someplace, and you can see how the lava flow has been pushed over so that it's almost vertical down at the bottom. And when we measured motion after 2018, a couple things we realized. Up here on the top, those pins were moving closer together by a lot. That's 6 centimeters, and those things are not very far apart. So, you know, they collapse together that amount. But the bottom half of this actually pulled apart. And it kind of has to do with the motion of what's going on with the 2 blocks sliding next to one another. We won't worry too much about that. If we look at the vertical motion down here, same type of thing. These guys kind of got pushed together, and that caused that pin to move up, right? There's B, there's C, there's E, there's F, right? These guys got pushed up relative to one another, and this one dropped down, right? Because it goes apart. So anyway, so we can look in some detail with how these faults move in different parts of the fault. Okay, Second thing that we kind of look at, and we'll give you an example from here, is to look at these level lines. So these are just nicely spaced. They're about, on average, right, or not on average, generally they're 300 feet apart. There are some extra ones in there as well. And they just cut all the way across the system. I'd just like to point out, just for a minute, sorry, how we doing? Pretty well. That everything north of about here on this line is so wildly vegetated that we're not going there anymore. We're not going to find anything in there. It's not really accessible, right? We're going to talk about things going on out here on this western level line because it's much less vegetated and a little easier to deal with. So we can see something about the relative motion across the faults. We can say something about how the blocks tilt. And we can also hopefully say something about how that's related to things going on this side. So just one other quick point. This is a little different style than some of these more modern techniques. So a GPS, permanent GPS station is in one place. And it's measuring things all the time from that one location. This is kind of nice because we're getting kind of a snapshot across the entire fault system and how it's moving. So that's a kind of a different type of information. So it's not like what we do. I mean, you know, a lot of these modern techniques are certainly, if we're going to give it some value judgment, better in the sense that it's giving us, some information. But this is, I think, still kind of an important tool because it provides a different kind of information for what's going on. And so, hopefully, Dave's here. Hopefully, it's useful for the folks that are doing things, right? And I think it is, right? I mean, that's why we keep doing it. All right. So when we go on these level line excursions, we got a couple other things that work pretty well when we do these projects, I guess. So one thing is the students understand, I think, a little bit about, what it takes to run a field project. You got to get outside. We're outside all day, right? The other thing is everybody's got a job, right? So Sadie's down here typing in the information. Richie's over here making sure that that rod is in the right place and doing whatever. We got some folks up the slope up here who are looking for the next points where we need to go, right? Somebody else is behind the camera here with another one of those rods, and then somebody, of course, is taking a picture. So we kind of have how we run the surveys. We have the need to have some pretty specific procedures in place, which is good for them. And then also, there's a lot of time involved. And this is part of the reason why the USGS guys don't do this so much anymore. They got day jobs. They have things they have to do, right? They're busy, right? I work for cheap. No, I mean, but we're able to fill a niche that's more difficult for the HBO folks to do, right? They used to do this a lot. Now they worry about monitoring all the other things they have to worry about. But it provides everybody with a good opportunity to kind of figure out how to work together, which is also a pretty important skill. Life skill, work skill, employment skill, I don't know, all those things, right? So we're out measuring these things, kind of running down the road. Okay, and there are some big faults, right? Again, some of this is just to show you guys what it looks like out there. So here's out to the west of the Hilina Pali Road. You can see that fault that's running all the way through here, the big fault. So part of the issue is when we're doing these different surveys, everything has to be one level line of sight after another. So it takes a while when you're on a steep slope to get those points connected. The other thing, if you've ever been out in the western part out there, it can be windy. And so it actually becomes a bit of a challenge to hold a 3-meter rod steady and level while we're making measurements. And these guys, again, do a nice job of making sure that happens. All right, so let's show you a little bit about what's going on. These are the first diagrams are from Don, and they are maybe some of the ways that things can move out there. So what are we looking at here? First things first, there are going to be some different scales on the vertical over here. So on this particular one, we're measuring relative to the north part of the line. And there's about 10 centimeters of total displacement from there back down to where the campground is and the road. So this is just two different measurements, one in August of 1968, one in February of 1970, so what's that, a year and a half, if I do my math right? And you can see Don has put in where the faults are, and some of the ramps and the like, and how things have moved. So this is a time when the caldera was inflating, and you can measure that by looking at how these pins move relative to one another. Here's a different measurement, and again, just as an example of this, here's a time when the caldera was deflating. And so now, again, we're pinning everything out to that north spot, and you can see there is some differential motion on some of these faults by a few centimeters, maybe a centimeter or two. But overall, there's about 5 centimeters of subsidence across that line in that time period. Again, and this one's about a year. So let's look at maybe a little bit longer term on this. And so now I've switched things a little bit. First things first, here is a diagram of essentially what the topography looks like. That's what the slope of everything looks like. So again, we've tried to put in where some of the faults are, right? But also you can see those faults are also in places where we have changes in the topography. All right. And so I'm now pinning everything out here to the campground, to the road. So here we go. That line that is 0 up there represents 1986. Between 1986 and 1997, I tried to pick time periods where we had pretty good information and about the same length of time. We mainly had caldera deflation overall. There were probably times when it was moving up and down. The scale's a little different here, right? So over that 11-year time period, vertically, that northern pin, about 2 miles away from the campground, subsided by about 80 centimeters. Centimeters. Do the same thing for the next time period. Again, tied to that 1986 starting point. So you can think of the space in between as being the amount of subsidence from 1986 to 2008, right? So, or 1997 to 2008, excuse me. But you can also see there's some wiggles in there, and those are some of these small movements along the faults. Okay, that's not all that interesting. It's okay. But notice that this last one, which I haven't put in here yet, in 2019. So this is after the big events in 2018. Magnitude 6.9 earthquake, collapses at the summit, right? All the rest of it. So that's what things looked like as a result of the deformation in 2018. And I want to just point out a couple things. So the road that was cut, right, is right along that thing right there. So whatever that is, 20-some centimeters. The other thing to point out here, though, that I think, again, we're trying to make this point, right? The same faults are moving when we get this motion. So you don't see a big break someplace in the middle. It's here. That's where it's breaking. It's here. And notice that this block moved up a little bit. Gee, that's a high spot. This block moved up a little bit. Gee, there's a high spot, right? So again, we're seeing that differential motion along those things as we're moving along. Okay? So again, this is now deflation, certainly, but it's also this coseismic, or in other words, in conjunction with earthquakes, right? Slip, differential slip along those faults. All right, one more. 2021, last year and a half ago, a few months ago, you might recall there was a big lava lake in Hawaii Mountain crater. There's now another one, right? One of the same one that's been reactivated. But that eruption started in September, right? Am I right?
Yeah.
September. Well, before that, end of August, there was a whole series of earthquakes that propagated away from the summit. A couple things that I think are interesting, may or may not. I'm speculating a little bit, but that's okay. Notice that this kind of comes down and then it kind of wanders across like this, and then it kind of comes down and it wanders across like this. And comes like that. Well, gee, where it wanders across off to the west, looks to me like it's in some of these places where some of these faults are. Yeah, it's hard to tell. One thing I think is true, however, here's the main bounding fault of this Kauai fault system. And notice how these things came down like this and stopped. I don't think that's a coincidence. I think that that's a big enough boundary that when the magma was pushing its way through there, that's what's causing the earthquakes, right? It ran into something. Okay. Well, fortunately, I have people that I work with that are students in our department who are willing to listen to me when I say, hi, would you like to go out and measure cracks and things this weekend? And they're like, sure, that sounds like fun. I don't have anything better to do. No, they have plenty of things that are better to do. But they come out and they do this a lot. So we went out, and this is approximately, right, where that level line goes. And we thought to ourselves, well, wait a minute. That level line basically goes right out to where those earthquakes are. So if you think about it, that's the dike, that's the magma moving below the ground out to the south. Well, gee, we happen to have all this information that goes on along a nice line like that. Huh. Let's see what happens. Okay, so a little background. Again, you guys are savvy as to what's going on with this now. So, I just picked two kind of typical 2-year intervals. One's 2010 to 2008. That was the last time it was measured before we went out there in 2018. And one was 86 to 90, or that should be 88. Oh, it is. Don't mind me. I saw 98. I got a little confused. 86 to 88. Okay, I just, there could have been other ones, that's fine. And I'd just like to point out that there's kind of some amount of subsidence, again, relative to the campground and the road and Hilina Pali Road and everything, on the order of, 10 or 15 centimeters, more or less, across that 2-mile long level. So we went out early September 2021, and we got that. So what is that? Well, that's what we kind of expect. That's what we were hoping to find, in fact. Over here, off to the north, that's where the dike's coming through. That caused the ground to move up like this. A couple interesting things. One, there's really no motion at all between 2019 and 2021, all the way across that first half of the level. It's almost none, which I thought was interesting. And I'll show you in a minute. But basically, there's a big fault. One of those big faults goes right here. So it's almost like it started to hinge up like this, and it found a spot right where it wanted to break and move like that. I mean, it's not very much, right? I mean, it's that much over about a mile, right? But it's, it works. The other thing that I think is, it's not, there's a little bit of a wiggle in there, right? But generally, those faults didn't move differentially. That whole block just kind of went like this, which is also kind of interesting. So anyway, so that's, we managed to figure out kind of how that worked. And one of the nice things, again, the motion here, what that does is that gives enough information from real life, from the ground, so that the folks at HBO can now say, oh, I can now make some sort of a model as to how much magma actually pushed through the ground to go out into this dike. Because they have some information from various points out there, but now they've got a very nice profile of what kind of half of that dike intrusion looked like. right? So they can use that ground truth to put into the model to try to figure out what's going on when that happened. Now, what could have happened there? Any ideas?
Fissure open up?
Yeah, we could have had an eruption down here someplace, right? And then it would have been nice to know kind of what's going on with that as well. It turns out that at these big shield volcanoes like Kilauea, what is it? It's about half. I think about half of the material that's coming up from the hotspot in the magma chambers basically doesn't erupt at the surface. So half of it's lava flows. Good rule of thumb, maybe. I'm making it up. And half of it is intruded into the volcano. So not every episode is going to create a lava flow, right? In this case, we injected new magma into the volcano. Didn't make it to the surface. So those are just a few of the types of things that we do. These are the real heroes, though, right? These are the guys that do all the hard work. I just kind of go out there and help. So, you know, a couple different groups of folks out making some of these measurements, and we've really been fortunate because we've been able to do a few things. And so this is just one of the photos. Nikki, I didn't have a photo of you and Bree. I don't know where it went. Or other folks, but you know, they've basically been able to go and again, one of the upsides of this is they've been able to go and present some of their information at Geological Society of America meetings, right? So they get a chance to go and talk to people and kind of tell them what we've learned at some of these places. So again, that's a nice kind of outcome from looking at this stuff. I've got a few thanks to all of those people, right, that are our geology students over the years, and I don't have enough slides to put everybody's name in there, so we'll just kind of collectively say hi to them. The South Dakota School of Mines folks, so Cheryl Gansecki, who's talking next week, Rick Hazlitt, who's author of the book, just in case you need a new book, if you're looking for presents, that's a good thing. They've been, a lot of the years, in the last few years, they have a field camp that they run out here twice a year, and they've been making some measurements for us. Don clearly introduced us to the fault system out there and really has done a huge amount of work, and super thankful for him for that. And Jim Anderson, who kind of is the person who got me interested in doing this leveling. We did a lot of leveling in the lower East Rift Zone. And really, he's the man that knows more about it than a lot of other folks do. So those are all some people to thank, and you know, I'm always looking for warm bodies to come out and help. So if anybody will just come ask me, and we'll go out and wander around on cracks. No, so we're gonna go out again. We're gonna keep doing this. We'll go out again and kind of go exploring and looking and seeing how things are going. So that's what I have for you guys. I hope I didn't go too long. And if you've got some questions, I'm happy to take them. Yes, sir.
Hi. So you mentioned how you use the data you gather out there to measure displacement along these faults. Are you ever able to translate that data into, say, like a volume or amount of magma that's moving underground?
I think for the dike intrusion, the last slides we were showing you, I think those guys did a little of that, right? Kind of pass it off to them to do that. Most of the rest of the fault motion out there, though, isn't from magma necessarily injecting in there. I mean, that's part of the reason why it's so great out there, right? Is that it's just moving in response to what's happening. So, but you know, that whole south flank, which is reasonably unstable on a long time scale, it's kind of nice to know how those faults are going to move, right? And there are times, Don's documented these, where there's been other types of magma injecting in there, and then yeah, it does fit into a model that would tell you kind of how much and where it's coming from. Yeah, good. Others? Yes, sir.
Hey Steve, how's it going?
Good. How are you, Norm?
Good. You know, you look at these measurements and you get to the third decimal place,
Is there like some background noise you have to work with? Does things kind of move a little bit? When does it become significant that, oh yeah, this is quite a significant change from previous measurements?
Yeah,
Does that make sense?
it's a good question, right? You know, I think out there, what would you say, Jim? If things are more than a couple, 2 or 3 millimeters, then we're pretty sure things have moved.
2 millimeters. Oh, wow. Okay.
And that's really the power of this, right? Is that if you guys have used GPS of any variety in your life, or on your phone, whatever, the horizontal is really good. The vertical is not as good, even with the high precision stuff, right? It takes a lot to get rid of that vertical precision. So this is really, because it's a direct measurement, it's pretty good. There are issues with heat shimmer, and if the wind's really blowing and everything's moving around, then it's hard. But yeah, I would say pretty easily we can see a couple millimeters. Yeah, good. You know, I mean, whether those decimal places in the millimeters,
Yeah.
but you know, that it's a little error averaging as well, I think. Yeah. Yes.
Do the faults act as barriers to dike flow? Could it go like this and then inflate?
I think it does. based on an N of 1, right? But yeah, I mean, I think if the dike comes that direction, I mean, Don measured some dike intrusions that kind of came parallel to the faults, right? And then it probably still interacts with that. I think those faults go down maybe enough that if it's a shallow dike, which I think a lot of these are, it's probably acting as some sort of a, don't do that, a barrier to the movement of that. I think in this case, because that earthquake storm went down like that, and then it really sat there for a few days and didn't go any farther. And that's why I think in that case it probably was, I think it had to have some influence. Yeah.
Hi. Referring to the origin of the Hawaiʻi Fault zone, I get confused sometimes when thinking about which came first. Is it, you know, as Kilauea was formed and inflating and having its eruptions and explosions, then the faults started to form, or they sort of formed with the rift zone, and then that contributes to the slides? And
Yeah, I'm confused by it too, so don't do that. No, I think one of the interesting things here, and Don has said this repeatedly, he's much more of an expert on this than I am, all of those faults and all of that information, all the way across that southern part of Kilauea, are all essentially going in the same orientation, kind of east-northeast, right? So it's almost like the faults don't recognize that the rift zones are there, right? So it has to be something that is kind of just related to that big volcano and the fact that that stuff's moving in response to having to move up and having it trying to move out into the ocean. So I think that's maybe one way to approach it, right? If you look at that structural grain, it's going through everything all the way across, and it kind of doesn't care that the volcano is there and erupting in terms of the volcanic products. Yeah?
Do you think if the rift zones weren't there, that you'd see that fault like all the way across the island? And it's just buried?
It is buried. I think, you know, I mean, the rift zones have to be there, right? But there are places further to the east that are buried by lava flows, right? But yeah, this particular spot is more that connector between the two rifts, right? So that's where much of that motion is occurring. There's other motion that's going on with the rifts. But it's all kind of in that same structural grain. I guess that's maybe the way to think about it. Because you can't, Does that kind of, does that help?
Yeah.
JP?
Yeah, I was just wondering if there was a digital elevation model with enough fidelity and precision, could you use your data to sort of make a 3D movie? How many minutes?
I probably couldn't. Somebody might be able to do that. No, I think, yeah, that's a good question. I don't know. You know, we've got a fair amount of cool information. How you make it move on. That works. Okay. Question?
Do you think that there would ever be
to work with it as kind of a dying methodology?
Yeah, it's a good question. Out there, well, just a different story. We had a whole network, Jim Anderson had a whole network of monuments down in the Lower East Drift Zone, 34 of them. 2018 was a big eruption down there. There are 11. Up at the park, some of the ones that used to be there are either buried in vegetation, or a couple of them are just out of the ground. And some of the old pins that were just nails and not stainless steel carriage bolts that got replaced, you know, they're going to rust and go away. I don't know. How's that? I don't know the answer. There's plenty out there right now, let's put it that way. It takes a lot to go measure all this stuff. Yes, sir?
When you're doing your leveling, are you often just measure vertical changes?
Yes.
Do you also do horizontal changes?
So at the crack stations, right, we're pulling stainless, or steel core tape because we're trying to get that kind of motion as well. For the level lines, we don't. That's all just vertical. Yeah, and it's
Kind of thinking of the big scale picture of the volcano and the magma, growth of the summit and something in the far south. Why is there that one region of north side down?
Yeah, I think that's, again, this is this kind of accommodation zone between the, I didn't say that very well when we were on it. It's the accommodation zone between the two rifts. So you basically have, that stuff is trying to slide down, so that's just that block in the middle that has to expand as that whole stuff is moving.
So does the amount of horizontal motion equal the amount of dike growth in the rifts?
I think out in the rifts it probably is pretty close, right? Because you don't have big giant rifts. So as that stuff is moving, and as those places have moved, you've had to fill it in with something. Yeah? So I think that's what that is. Yes?
So, it's 8 o'clock and everybody probably needs to go home and eat dinner and get some sleep. But if anybody else has extra questions, Steve will be around here for hours. But like I said, we'll see you next week for Cheryl Gansek's talk, and how about another round of applause for
All right, well, that was the speech. Next one we will be bringing to you live on Saturday from Ocean View. That'll be at 1 to 3 p.m. and we'll be with the USGS and Civil Defense going over kind of debriefing from the Mauna Loa eruption. So hope to see you guys there. Thank you, Two Pineapples, for
Thank
doing
you.
this.
1 p.m. Hawaii Standard Time.
Oh, 1 p.m. Did I say 2?
No, but Hawaii,
Oh.
just Hawaii time so everybody knows.
Right.
Yeah.
So yeah,
Right on.
until next time, aloha.
Aloha. Thanks for joining us. Anna's over there. It's only 7:15.